Here we go. Now, when is a trig identity not defined? When is a trig identity not defined? So the first thing we need to do is we quickly need to talk about a trig identity. Now, a lot of people, when you see this equal sign, you seem to think that this could be an equation because it has a left-hand side equal to a right-hand side. But this is not a trig equation, so this is not a general solution because of this word right there. Prove it. Prove it means show that the left-hand side will always be equal to the right-hand side, no matter what the angle is. And I don't know if you picked this up when you were doing trig identities, and by the way, you're not allowed to prove your trig identities like this. I'm just showing you what a trig identity actually means. If I go and I pick any angle for theta, somebody pick an angle. It can be as random as you like. 43. I had 43. Okay. Was it 43? 23. Okay, we'll pick 23. So if I pick 23 and I put it into the left-hand side, so I'm going to do this. I'm going to go 23 equals, and I'm going to go shift, store it under A, so that every single time A comes up, it's going to be 23 degrees. So if I put this on the left-hand side, and I say it's cos of that angle squared plus 2 cos of that angle plus 1. And then I put it over sine of that angle squared, so it's going to be sine of that angle squared. Then on the left-hand side, I get a value of 24,1587. And I'm going to just write that down somewhere so we can compare it just now. So I'm going to say 24,1587 ... Now, if I go to the right-hand side and I type in this exact same angle on the right-hand side, so I go 1 plus cos of that angle over 1 minus cos of that angle. (24,1587,864), which means the left-hand side is equal to the right-hand side for 23 degrees. But why was I willing to pick 23? Because any angle will work here. This is why a trig identity is not an equation. An equation, like the ones we've been doing, the general solutions, has a formula for the angles that work. Meaning, when you solve one of these general solutions, so if I go back to, for instance, this one, that one. So if I solve this one, then 21,8 will make the left-hand side equal to the right-hand side. If I add 180 or I subtract 180, or if I add and subtract multiples of 180, the left-hand side will be equal to the right-hand side. But if I again pick a random value like 15, that will not satisfy the equation. That will not make the left-hand side equal to the right-hand side because only certain values satisfies this equation. Do you understand? So this is why this is called a trig equation, and this is why you are asked to solve for theta. Find the values of theta that makes the left-hand side equal to the right-hand side. Whereas a trig identity, that's not the case. A trig identity, any and pretty much, we'll talk about just now the all values, because it's not always going to be all values, but pretty much any and sometimes all values will make the left-hand side equal to the right-hand side. So you don't find theta here, you just prove that I can simplify the left-hand side so that it becomes the right-hand side. There's no solving for theta here. Do you understand the difference between an identity and a trig equation? Okay. Now, this is why we split it into the left-hand side and the right-hand side. Because I need to go and take that left-hand side and I need to simplify it until it looks like the right-hand side. And then remember, my deduction says, therefore, because the left-hand side is equal to the right-hand side, this will always be true. And please, people, if you don't split it left-hand side, right-hand side, if you just put this down, if you start with that equal sign in the middle, we pretty much call that a breakdown because that means you do not understand an identity. You don't understand an identity. We're trying to prove it. You can never in mathematics start with what you're trying to prove. You have to end with what you're trying to prove. Got it? Okay. So, now, I'm sure Mrs. Prince spoke to you guys about proving trig identities. I always say to people that you have a little toolbox for solving trig identities. And there are only 5 tools inside that toolbox. The tools are pretty much use the tan identity. That's the one tool. Use the square identity. That's the other tool. Simplify fractions, which generally involves an LCM of the denominator, which means algebra, simplify the fractions. Factorize, because that's always a tool in algebra, so here it's also a tool. And then lastly, the last little one is something I call the Batman move. The Batman move. But you hardly ever need the Batman move. I will go and, when we do revision later on, I'll show you an example specifically where the Batman move is required. You go like, the Batman move? What do you mean? Okay. Anybody who's a fan of Batman will know Gotham needs you. And this is where Gotham needs Batman. Okay. So that 5th one hardly ever happens. That's when you send up the bat signal because you can't do any of the other in your toolbox. So like I explained to you, right there on the left-hand side, I look at that and I go, that looks like a pretty decent factorization there at the top. Can you spot it? Now, it's amazing how often people can't simplify identities because they can't spot the factorization. So sometimes you just need to write it in a different format. You need to go k squared plus 2k plus 1. So if I ask you to factorize that one, what would you get? K times k, you agree? 1 times 1 and plus, because this gives you k plus k is 2k. So that means if that factorizes into this one will then factorize into cos of theta plus 1 and cos of theta plus 1. Because like I said, one of the 4 tools in your little toolbox is factorization. So please, please, please remember factorization. Trinomials, highest common factor, difference of squares. Those are all valid factorization techniques here. Then we look at the bottom and we say, good, I've used my factorization tool. Remember I told you there are only 4 tools. Factorize, tan identity, square identity, and doing the algebra, which generally involves simplifying fractions. Now what do you think at the bottom? Which one of those 3 remaining tools seems like a good idea here? Square identity, because it's sine squared theta, which means I can use my square identity. So sine squared theta becomes 1 minus cos squared theta. And then what can you see at the bottom? Which one of my 4 tools is going to work perfectly over here? Factorization, difference of 2 squares. So, and by the way, you can write that top as cos theta plus 1 squared. I'm not going to write it as that. I'm going to keep it like this. You'll see just now why I do that. And then that's going to be the difference of 2 squares, which means it's 1 plus cos of theta and 1 minus cos of theta. And what can I do now? I can simplify the fraction. Remember I told you one of your 4 tools is simplifying the fraction. So I can go and I can say that divides into that, which means, and now take a look at where I'm headed. That's 1 plus cos theta, because I'm allowed to swap the order around there without changing the signs, over 1 minus cos theta, and please don't forget to end your trig identity by stating it's equal to the right-hand side. Don't forget to do that, otherwise you haven't proven the identity. So like I explained to you, this is not a general solution. This is not a general solution. This is a trig identity, which will always be true, or will it? There's the question. So sometimes what they do when they ask you to prove a trig identity, they do a follow-up question. And the follow-up question says, great, you've now proven the left-hand side will always be equal to the right-hand side. And whether I substitute 23 in there, whether I substitute 43 in there, whether I substitute 62 in there, it doesn't matter. It will always make the left-hand side equal to the right-hand side. It's always true. You've proven it. But the follow-up question will then go and say this. Determine the values of theta for which this identity is not defined. Meaning, there are certain values of theta that if I sub it into the left-hand side and into the right-hand side, will mean I will get a math error on my calculator. And if I get a math error on my calculator, then obviously it's undefined, which means I can't sub that value into the left-hand side. I can't sub that value into the right-hand side. So that value, the identity will not work for it. Got it? So when we want to determine the values of theta for which the identity is not defined, we have to remember the following. Identities are undefined in exactly two circumstances. The first one, there's a fraction in the identity. So somewhere in the identity there's a fraction, and please remember, what about fractions? The denominator can't be equal to 0. So if the denominator in a fraction is equal to 0, then obviously the identity will be undefined. Because if you put that into your calculator, if you put a 0 denominator into your calculator, the calculator will go math error. Got it? And the second part where the identity is undefined has to do with the tan identity, or the tan function, I should rather say. Remember when you were drawing trig graphs? What can you remember about the tan graph? Why is the tan graph so different from the sine and the cosine graph? Asymptotes. Now, what did you think those asymptotes were? An asymptote is a place where something is undefined, where it can't go. It's like an electric fence. Don't touch it. Got it? So the tan function at certain points in time is undefined. And specifically, it's undefined for 90 degrees plus k times 180. Because if I go and I type 90 degrees into my calculator, so I type in the tan of 90, I get a math error. And there's a very good reason for it. There's actually a very, very brilliant reason for it. If I go and I look at my special angles, let me just find this for you guys. And I did draw my special angles over here. Where is this now? There, special angles. So if I look at 90 degrees, there's the values for 90 degrees. There's x, there's y, and r is always equal to 2. So please remember, tan puts y over x. Y is 2. X is, whoops, 0. That's why the tan of 90 degrees is undefined, because the tan of 90 degrees is 2 over 0. And this, people, is what we refer to as the general solution for the tan asymptotes. If I draw all of the tan asymptotes in a tan graph, my standard tan graph, then all of those asymptotes will have that general solution. Got it? It'll be at 90. It'll be 180 degrees later at 270. It will be at 90. It will be 180 degrees earlier, which would be at minus 90. Those are all my asymptotes. Got it? So, this, you're going to memorize it. You're going to memorize and write it down. Meaning, if you have an identity that has the tan function in it, you immediately write that down. You don't have to go and do any calculations. You just write that down and you get a mark for it. This one, however, means you're going to set the denominator equal to 0, which means you have to solve a general solution. You have to do a general solution here. This requires a general solution. So in this particular example we were busy with, if they go and they ask, not to prove that, they just ask, for which values of theta is the identity undefined or not defined. So that's the question. For which values of theta is the identity not defined? So all you have to do is you first check for tan. Nope, 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 nope. There's no tan in this, so I do not write that down. I only write that down if there's a tan theta in my identity. But there are fractions. So now, because there are fractions, I have to go. Did it switch off? Sorry. Apologize, I didn't check. Just let them know it's being recorded, so it's fine. Like you said, too many things to check. Okay. So, in this one, because they are fractions, and by the way, this is the interesting thing about these. You can set sine squared theta equal to 0. Because obviously if this is 0, then the identity is undefined. And you can then go and set 1 minus cos theta equal to 0. And by the way, 99% of the time, these two will end up giving you the same general solution. Why? Because we know the left-hand side is equal to the right-hand side. And because the left-hand side is equal to the right-hand side, generally, not always, but literally 99% of the time, you don't have to solve both general solutions. They will give you the same general solution. I'll prove it to you guys. Okay, so what do we have there? We have a general solution. So to get this spot where the identity is undefined, we're going to say, first things first, square root both sides. So if I square root both sides, I have sine theta is equal to 0. I find a reference angle, and by the way, you'll see your reference angle is going to be 0 degrees, because if you do inverse sine of 0, you end up with 0. So your reference angle is 0 degrees. And then you can go and you can say sine has got two parts. The first part, we say theta is equal to 0 degrees plus k times 360. And please remember k is an element of the integers. And the second part, theta is equal to 180 minus 0. Now, by the way, I'm not going to write down 180 minus 0. But no, I'll write it down. It's fine. Otherwise, there's going to be bound to be somebody who's going to go like, what happened there? You don't have to, though. Please don't. You don't have to write this down. Okay. So this one, obviously, will then just be k times 360. And this one will then be 180 degrees plus k times 360. But I have discussed this one with you before. I said a lot of the time in the textbooks, they don't write it down as two parts. You can just go, remember I spoke to you guys about this before. If you just write down theta is equal to k times 180, it means this one thing means exactly the same as those two things. Means exactly the same thing. Got it? Now, if you did go and you took this one further, just to prove it, this, by the way, not necessary. This is not necessary. And I'll explain to you just now how you are actually going to know the other one is not necessary. Here we can then go and say that cos theta is equal to 1. And what's my reference angle going to be there? Look. My reference angle is 0. So the moment my reference angle is the same here as it is there, please stop. Please stop. You don't have to go any further because you will end up with the same general solution. So this part, the moment you see that, you can stop. Stop. The only time you will continue is if your reference angle here is different to your reference angle there. Then you'll continue. Got it? So, let's quickly take a look at this one. Now, I don't want you to prove the identity here at all. That's not the question. The question is just determine the values of theta for which this identity is undefined. So remember, we always look at two situations. The first situation is we check, is tan anywhere in the identity? Yes, right there. So the moment tan is in the identity, you memorize and you write this down. That is the general solution for the asymptotes of tan. So you just write that down. Memorize, write it down. Then, second part, is there a denominator here? No. So I'm done. I'm done. That's it. Got it? So the first one, I didn't write that down because there was no tan identity in it. This one, I didn't set a denominator equal to 0 because there was no denominator. So with this one, it required some extra work, but any multiple of 180 is not going to make the left-hand side equal to the right-hand side because I'm going to get a math error, and I'll prove it to you. Just quickly, look. If I go cos of 180 squared plus 2 cos of 180 plus 1 over sine squared of 180, then I get math error. And that's what this is about. It's about saying for which values of theta will the left-hand side not be equal to the right-hand side because the identity is undefined. That's pretty much it. Okay, right, let's try one more. Okay. So, first things first, is there tan in this identity, yes or no? Yes. So you immediately get points for this. And again, they ask for which values of theta will the identity be undefined? That's the question. And immediately, because there's tan, you can write down the first one is where theta is equal to 90 degrees plus k times 180, which is my general solution for the asymptotes of tan. You'll immediately get marks for that. No calculations needed because tan is present in the identity. That is one of my restrictions. Okay. But I now have to go to the second part because they are, in fact, fractions. So the moment there are fractions, I have to say where the denominator is equal to 0, so where 1 minus tan of theta is equal to 0, that is definitely going to be one of the places where this identity is undefined. Now, by the way, you could also have written down where sine theta minus cos theta is equal to 0. This one will again give you the exact same general solution. Setting that equal to 0 will give you the exact same general solution as this one. And you can check it, but it's really not necessary. Okay. So, specifically in a test or an exam, I look at the mark allocation. If the mark allocation for this sum is 4 or less, you will never have to set both of those equal to 0 and solve it. You will only ever have to set one of them. But the moment it's more than 4, or I should rather say if it's 4, if it's less than 4, you only have to set one of the two equal to 0 and solve. If it's 4 or more, you might have to set both denominators equal to 0. But this one's also pretty easy. It's going to be where tan theta is equal to 1. My reference angle here is going to be 45 degrees. You can check it out. This is one of my special angles. So that's going to be 45 degrees. And then I can go, it's where theta is equal to 45 degrees plus k times 180. And just to prove to you that I'm not making this up, you don't have to. Again, this is not necessary. Definitely not necessary. But if I go and I set the other denominator, the sine of theta minus cos of theta equal to 0. then this is one of those where I have only sine and only cos, and the angles are the same. So what am I going to do? I'm going to say sine theta equal to cos theta, and I'm going to divide both sides by cos theta, and what do I end up with? I end up with tan theta equal to 1. And that, people, is why this is clearly not necessary, because you're going to end up doing double work. So literally 99% of the time, if the fraction contains more than one, sorry, if the identity contains more than one fraction, you don't have to set every denominator equal to 0. You generally only have to set one of the denominators equal to 0, and that will tell you where this identity is undefined. Got it? So, not too bad. Okay, let me just stop this recording.